Good afternoon, folks. Everybody hear me?
Yep.
Great. All right. So today we're going to be really diving into Markov chains and learning what they are and the sort of fundamental theorem of Markov chains. And then we will be spending the rest of the lecture looking at random walks on graphs, which are a particular interesting kind of Markov chain. So I started to introduce Markov chains last time. We have a state space, S, and we have a Markov chain that starts in a start state, x of 0, and then transition.
I don't see any whiteboard.
You don't see any whiteboard. How interesting. Thank you for telling me. Let's try this again. There we go. All right, so we start in the start state x0, and then we carry out transitions to a series of states indexed by some time t that goes on forever, where we write Pij to be the probability that xt plus 1 is equal to j, conditioned on xt being equal to I. Okay, and the point is that this quantity Pij is independent of t. Okay, that's the case for our simple Markov chains. And the other important thing is that xt plus 1 depends only on xt. Okay, and this is known as the memoryless property. The Markov chain doesn't care how you got to xt. It doesn't matter what the path was. All that matters is that you're at xt, and that determines your probability of transitioning to any other xt plus 1. Okay. Now, so that defines all of the transition functions, all the transitions. The initial x0 may be fixed, or any chosen distribution. It turns out that for all of the interesting questions about Markov chains, it really doesn't matter what the initial state is, because what you're interested in is the long-term behavior over time. And in a sense that we will formalize, the memoryless nature of the Markov chain means that eventually you can't even remember what the initial state was or what distribution it had. It has no impact on the long-term behavior of the Markov chain. Okay. So we can take all of these transition probabilities Pij and write them as what is known as the transition matrix to encapsulate that. And if Qt is a vector representing the probability distribution of x of t, right? In other words, Qt sub I is the probability that xt is equal to I. Then the probability distribution for xt plus 1 is just equal to q times that transition matrix, p, right? Because qp sub j is just equal to the sum over I of the probability that you were in state I times the probability that you transition from state I to state J. Okay. Good. So that gives us sort of an algebraic characterization. Also note that the probability distribution for xt, just by applying this repeatedly, is just equal to the initial probability distribution times the teeth power of the transition matrix. So that's the algebra, but I don't like algebra. I like combinatorics. So we can think about a graph model for a Markov chain where there's a vertex per state and an edge, ij, whenever pij, the transition probability, is greater than 0. And you, of course, can put pij as the weight on that edge. Okay. Note that this means that the weighted out degree of each vertex is equal to 1, right? Because the probabilities of transitioning out of I to some state have to sum to 1. Okay. And notice also that what do possible state sequences correspond to in this graph?
And paths?
Yeah, I'm going to say walks because these are possibly not simple. Right, so a state sequence can loop back on itself pretty much arbitrarily, and so I'm going to use that broad term of walks, except sometimes I'm going to forget and say path, but you should remember that it doesn't have to be a simple path. Okay, so these graphs I think are very helpful for intuition about what's going on with the Markov chain. It's that we're just walking on some path. We're just walking through the graph through a series of vertices. Now, possibly the most important definition around Markov chains is the notion of a stationary distribution. A stationary distribution is a pi such that pi times p is equal to pi. Okay, in other words, it is a left eigenvector of value 1, of eigenvalue 1. Okay. So what's interesting about a stationary distribution if we're thinking about Markov chains? Why is it called stationary?
Because like the distribution doesn't change.
Exactly. So if xt has this stationary distribution, then so does xt plus 1. Okay. So obviously, you know, a Markov chain does not need, like, the Markov chain does not stop evolving state, right? You don't just stop in one state, but you stay in one distribution of states, no matter how long the Markov chain runs. So time kind of doesn't matter. Okay. So stationary distributions are interesting. All right. So the question is, when do they exist? Okay. Under what circumstances? So let's take the graph picture and think, what do we need to rule out? What kinds of graphs, if you imagine a graph that you're walking on, randomly. Actually, I'm not only going to talk about ruling them out, but, or sorry, let me add another question. Let me ask, are they unique? Okay. So maybe a graph, maybe a Markov chain has two different stationary distributions, which would be disappointing. It's kind of nice to imagine that there would be just one. So what kinds of weird situations might we want to rule out in thinking about graphs if we kind of wish that graphs had stationary distributions and that they were unique? Well, one thing that works against having a stationary distribution is a graph like this. Okay. If I just have an infinite graph that points off to the right, okay, what's the long-term distribution of states if I start on the left?
All zeros?
Well, it's never all zeros. It's just that it's always one on a single vertex, right?
Yeah.
But the point is that where it's one keeps changing. So there is no stationary distribution here. Right? Because it never settles down. Now, another interesting situation is something like this. Actually, let me start with something easier. So what goes on with this graph? If I start on the left? Well, if I start at x0 equal left, then what happens is I run this Markov chain. Well, I keep alternating. So again, things don't settle down, right? I'm not going to ever end up in any kind of stationary distribution. I'm just going to keep going back and forth from left to right.
A quick question.
Yep.
So, I mean, doesn't the stationary distribution exist for this? It's like, you know, half. It's just that the eigenvalues are not like
exactly
like they live on the
what
unit.
we have here is a network where there is a stationary distribution, but it's never going to happen if we start from the wrong state. Start from the wrong distribution. Okay, so in the first example, it's just never going to happen. Doesn't matter how you start. In the second example, it's going to happen if you start in the right distribution, but not otherwise. Right? Now, here's another example. Okay, what if I have this graph, which consists of 4 vertices? Well, if you think about it, in this graph, there are 2 distinct stationary distributions.
Wait, why are there only 2?
Sorry, there's, let me say, greater than 1. Okay, it's not unique. Okay, because right, if I start on the left half, if I do half on the left, then I'll always be on the left. If I do half on the right, I'll always be on the right. Each of those is a stationary distribution. There is more than one. Okay. So it turns out that these are the 3 troublemaking situations. And if none of them apply, then we have a very powerful result. Okay. But in order to give that powerful result, I just need to do a few more definitions. So the first is irreducibility. Okay. So irreducibility is simply saying that any state has a path to any other. Okay. Irreducibility is the term that's used in Markov chains, but we have a different term in computer science, which is, what do we call a graph if every vertex can reach every other vertex?
Connected.
Well, that's a term we use for undirected graphs.
Oh, right. Yeah, yeah.
All right. But here, Markov chains are, in general, are directed graphs. So this just means strongly connected. Okay. The other thing I need to talk about is persistence and transience. So define Rij of t to be equal to the probability that the first arrival at j is at time t, conditioned on starting at I. Okay. So notice that the way I've defined it, these are probabilities. They sum to at most one because they represent disjoint events. Do they always sum to exactly one?
Maybe only if it's irreducible, or if you can reach.
Right. Well, so there is this issue of reaching, right? And in particular, you might never get there, right? So I'm going to define Fij to be equal to the probability that you eventually reach j from I. And so that's just equal to the sum over all t of the Rijt. I'm also going to define Hij to be equal to the expected time it takes to reach state j starting from state I. And so that's just equal to the sum of t times Rijt, right? And now that I've got those quantities, I can give you the definitions of persistence and transience. So if Fij, if the time that if Fij is less than 1, what does that mean in English?
There's some probability that we never reach j.
Exactly. There's a chance we never reach j, which means that the expected time to do it is going to be infinite. Okay. But the converse may be not true. All right, you can have, at least in infinite Markov chains, these paradoxical situations where you know that you will eventually reach a state, but the expected time to do so is infinite. And so now finally definitions. If sorry, let me write the definition first. We say a state is transient if Fii is less than 1. So what does Fii less than 1 mean?
There's a chance that you'll never return back to your current state.
Exactly. There's a chance that once you leave I, you'll never return. The converse is a state is being persistent, which says that the probability of a return is equal to 1, that you're guaranteed to return. Okay? If HII is infinite, if you're guaranteed to return, but it's going to take infinite time, we call that a null persistent state. Okay? And if you think about it, this is a partition into 3. Every state is either transient or null persistent or non-null persistent. Okay. So let's understand these notions of persistence and transience in finite graphs. So if we're talking about our normal graphs, our directed graphs, what makes a state, if we're going to be then taking a walk on this graph, what makes a state persistent or not, or transient?
It's just always persistent if it's connected, right? Strongly connected.
Strongly connected. Okay. So you're saying if a graph is strongly connected, then all the states are persistent.
Sorry. It's a property of a point on a graph, not it.
Exactly. But in fact that is correct. If a graph is strongly connected, all the states are persistent. Okay. Why is that?
So from any point, there's some positive probability you'll get back to that point I.
Exactly. So from any j, right, there is the probability that you return to I in some number t of steps is greater than 0. So you can think about trying that experiment, right? You're at j, you try running for t steps and you see if you return to I. And there's a non-zero probability that that will happen. Okay, which means the probability that it fails is less than 1. Now, if it fails, then you're going to be at some other state. But that state also has a non-zero probability of returning to I. So I can run another experiment of seeing if I return to I from that state after a certain number of steps, right? And that also has a probability less than 1 of failing, right? And I can just keep on running these experiments over and over again. I run for some appropriate number of steps and see if I have arrived at I, and there is a probability less than 1 that I fail, okay? But the Markov chain runs forever. So I'm going to be multiplying together an infinite number of experiments, right? So each attempt fails with some probability less than 1. And I'm going to repeat this experiment infinitely often. So the probability that I never return is 0. Okay, it's 1 minus epsilon to the infinite power. In fact, I can say that all of these states are non-null persistent. okay? Because whatever your graph is, this epsilon is some fixed number, right? There's a smallest probability of a path of a given length, right? And so your probability is bounded away from 1 in each attempt. And that means that we can think of this as a geometric random variable, right? The number of tries, the expectation for the number of tries is like 1 over epsilon. So it's finite. Okay. So that's true if a graph is strongly connected. But what about the other graphs? Well, we've already seen that strong connectivity is pretty important, right? So let's imagine that we find the strongly connected components. Okay, here's one, here's another, here's some more. Okay. The edges outside these strongly connected components form a directed acyclic graph. Okay. Why is that? Why do I know that there are no cycles from
Because
these?
then you could merge strongly connected components.
Exactly. If there was a cycle here, I would merge those strongly connected components into a bigger one. So I have this DAG. Okay. Now, if I imagine taking a random walk through this DAG, what is going to happen? Well, suppose I start in this strongly connected component. I'm going to noodle around in it for a while. But what is eventually going to happen?
You'll jump ship probably.
I'm going to leave. Okay. Once I leave, what can I say?
You'll never return.
I'll never return. No, I'll never return. Right? So because it's a DAG, once I leave, there's no way back. I hope some of you got that reference because we are in Boston, so it's important. So where am I going to end up in this graph that I've drawn? If I wait long enough.
Bottom right.
Yeah. I'm going to end up in what's called this final component. A final component is one with no outgoing edges. Okay. And what I can say is that any vertex in a final component is non-null persistent. Because really, once you're in that final component, it's just the strongly connected graph case that we already analyzed. Okay. Any in a non-final component is transient. And the reasoning is the same as before. Essentially, there is an edge leaving, which leaves from some vertex in the component. And there's always a non-zero chance that I will arrive at that exit vertex and take the exit edge. And so if I run forever, this thing which has a non-zero chance is going to happen eventually with probability 1.
A quick question.
Yes.
How do these definitions work out if they're like multiple final components that are not like connected to?
That's fine.
Okay.
Every vertex that's in a final component is persistent, is non-null persistent. Because remember, persistence is asking, if you start in a vertex,
Oh.
do you come back to it? So
Gotcha, gotcha.
even with multiple components, if you start in one of them, you'll stay in.
Cool.
Okay? All right. One more definition. Sorry, two more definitions. So the other thing that we saw, so this whole issue of final components and transients, that's really what's going on in the first example with the graph that's marching off to the right, right? It has no strongly connected components, and that makes all of its vertices transient. Okay. So now I'm going to look at the other case where you have these back and forths, and that takes us to the notion of periodicity. The periodicity of a state is equal to the maximum time value t such that the state, sorry, do I want the maximum there? No, I want the minimum, sorry. It's the minimum t such that the state only has Rij t, sorry, Rii t greater than 0 when t is equal to some constant a plus big T times b. Okay. No, actually, sorry, I take it back. It is the max. I was wrong. Okay. No, it's the min. Sorry, I don't know why I'm flip-flopping on this, but it will become clear as we look at an example. So in sort of the nice case, right, if you're at a state at a particular time, you can kind of get back there at any time in the future. Okay. But if we look at the cycle, right, these states have periodicity too. Okay, right? If I start at time 0 at the left state, then I can only get back there on even time steps. Okay. And so a state on a graph, a state has a period t if all cycles containing the state have a length that is a multiple of t. Okay. And as we saw above, cycles are another problem for stationary distributions because there are these situations where you can just keep moving back and forth. And so at different times, your distributions are different. And they never settle down. Okay. Now, these are actually, periodicity is actually easy to fix in graphs. What you do is you add self-loops. Okay, so if I take this graph, okay, which has a cycle, and I just add an edge that loops back to each vertex, I claim that in this graph, there are no periodicities larger than 1. Okay. And if you think about it, a self-loop is just allowing the Markov chain to pause with some probability in every time step, right? It may sit where it is instead of moving on. Okay.
Quick question.
Yes.
Should it actually be max? Because if it's min, can't we just set t equals 1?
Yes, you're right. It is. Sorry, I keep wishy-washying on this, but it is the max, right? So the period of the original cycle was 2, because you could return in any multiple of 2, but you couldn't return in the odd numbers, right? A cycle of length 4 will have period 4 for the same reason.
Mhm.
Okay. All right. So that is really the last thing that we need to talk about. So now we just have a definition that puts things together. We say a state is ergodic if it is aperiodic, that is, has period 1, and non-null persistent. Okay. So if you have an ergodic state, that means that at least at some point in the future, it could be at that state at any point which is sufficiently far in the future. Okay, it's not excluded from any distant future time. And so that gives me all the definitions that I need to write the fundamental theorem of Markov chains. Which is that any irreducible, finite, and aperiodic Markov chain satisfies the following statements. All the states are ergodic. No state is periodic, and every state is non-null persistent. Second, there is a unique stationary distribution. Pi. With all of the probabilities non-zero. Third, the states are all non-null persistent. You always come back to every single one of the states. And the time that it takes, the expected time is just 1 over the stationary probability for that state. And finally, the limit as t approaches infinity of the number of visits to state I divided by t goes to t times pi sub I, kind of a central limit theorem, or a law of large numbers for Markov chains. Okay. And all of these are very easy to see, except for the uniqueness, right? I've kind of already taken you through the argument, thinking about graphs, about why, if this Markov chain is finite and irreducible, which means strongly connected, and aperiodic, that means that all the states are ergodic, that there's no way for that you're always going to come back to all of the states, right? We made that argument for the strongly connected case. And because it's aperiodic, there's no restriction on when you come back. It could happen at any time in the future, you could be back at the state you started at. Okay. The fact that the stationary distribution exists and is unique takes more work. You actually, those of you who took 6854, depending on the year, you may have actually proven this. It is something that you can prove using linear programming and duality from linear programming. There are various other ways. It's basically a linear algebra statement that any stochastic matrix, so a matrix whose rows sum to 1, has an eigenvector whose eigenvalue is 1, and all of whose coordinates are positive. Okay, but I'm not going to prove that because it's just math. So it's not interesting from a randomized algorithms perspective. The fact that the hitting time is 1 over the stationary distribution just follows kind of by the law of averages, right? So if pi I is going to be the probability that you're in state I, okay, then expectations tell you that you're going to be in state I a fraction pi I of the time steps, right? And so on average, that's going to be every 1 over pi I time steps. And so the average spacing between those arrivals is pi I. Make sense? So the number of times that you're going to be in state I is t pi I, because this is just an expectation, right? Sorry, I have an extra t here. So if the probability that you're going to be in state I is pi I, then over t steps, it's going to be that you expect to be there t pi I times. And that just means that the spacing, the average spacing between them, which is this quantity HII, is going to be 1 over pi I, just so that there's the right number of them. Okay? So that's the fundamental theorem, and that's the thing that we rely on whenever we're looking at Markov chains, is we can immediately say, once we check these very simple conditions, that there is a unique stationary distribution. And a lot of times that's all we need, that it exists, and we can prove all sorts of interesting things. At other times, we will show a particular distribution is stationary, and we will then be comfortable that there is no other stationary distribution. Okay. Now, a sort of a corollary that I'll talk about next time is that over time, the distribution converges to the stationary distribution. So no matter what state you start in, if you run for long enough, the distribution of states will approach the stationary distribution. And this again has to do with the memorylessness of the Markov chain, that it can't remember how things started. And so the stationary distribution is really the only place that it can settle down. Okay. All right, so this was a lot of definitions and a theorem. Does everybody feel like they're on board with what we have so far? So now I'm going to start studying a particular interesting case, which is random walks on undirected graphs. Okay. So I talked to you about this sort of general mapping between a Markov chain and a directed graph. Okay. But if you start with an undirected graph, that defines a natural Markov chain, right? You take any undirected and non-bipartite graph, right? And I'm going to say that it's non-bipartite so that I can know that it's aperiodic. All right. If the graph is not bipartite, then you can prove that there is no period greater than 1. Okay, and that means that the fundamental theorems are going to apply. And now the transitions are that on each step, you choose a random neighbor. And that defines your Markov chain. Okay. In other words, the probability that you transition from U to V is just 1 over the degree of u. Okay. So everybody understands the Markov chain we're looking at? So actually, in this case, it's very easy to identify the stationary distribution. Pi sub v is just equal to the degree of v divided by m. Sorry, 2m. Okay. What's the reason? Well, we just check. Okay. So we have that, or we're asking whether pi sub v is equal to d of v divided by 2m. Well, but what do we know is the definition of pi sub v? It's the sum over all u of pi sub u times the probability that you transition from u to v, which is 1 over d of u. Yes? But I'm positing that pi of u is just d of u over 2m. So I'm just summing 1 over 2m over all of my neighbors, and so I get d of v over 2m. And so this particular distribution, which says your probability of being on a vertex is proportional to your degree, satisfies the stationary distribution definition. And the fundamental theorem says that it is the only stationary distribution. Okay. And you immediately get interesting things from this. In particular, you find out that that HVV, the time that it takes to get back to a vertex after you leave it, is just equal to 2m divided by the degree of v. So this is pretty interesting and not at all obvious, right? That if I start on a vertex and start wandering around, I'm going to get back to my starting point in linear time. Okay. So, everybody with me so far? Let's look at some more interesting things about these undirected graph walks. So, we've already talked about the hitting time, HUV, to reach V from U. I'm also going to define the commute time. CUV to be equal to, no, I shouldn't use C, I need that for something else. Actually, I'm not going to talk too much about the commute time, so I won't use up a letter for it. It's just the time to go from U to V and then back from V to U. Okay. Next, I'm going to define the cover time, C sub U, for a graph G, to be equal to the expected time to visit all the vertices of G, starting from U. And the overall cover time, C of G, to be the worst cover time over all of the vertices in the graph. So how long is it going to take me to visit the entire graph just by wandering around? Pretty natural question. And it actually has algorithmic applications, which I'll get to in a minute. So now that I've defined this quantity, how big can the cover time be? Starts to sound algorithmic and interesting, right? So let's look at some examples, okay? So suppose I have a clique, okay? So what's the cover time of a clique? So what does the Markov chain on a clique look like? What do you do in each time step?
You move to a random other node.
You move to a uniform random other node. So in each time step, I am going to a random vertex. And what is the definition of the cover time? That I have encountered every vertex. So what problem formulation am I asking? I'm asking, if I move to a random vertex each time, how long does it take me to reach every vertex? Coupon collecting, right? So I have this very shy person who only sends me notes, and nobody else can see them. But he's always right. Every single question I've asked, he gives the right answer. So yes, this is a coupon collector problem. So what's the cover time going to be?
N log n.
N log n. Okay. How about a line? How long is that going to take to cover? What do you suppose is the worst place to start?
On an edge, right? I don't know.
What was that?
On an edge,
What do you mean an edge?
like starting either left or right.
Oh, at the end, at a far end. Yes. So the worst time is to start is at a far end. But then how long does it take to get to the other end?
Square root n. This is deviation.
Square root of n. What do you mean by
Oh
this?
no! Oh, sorry. Yeah. Sorry. No. Okay.
You know, you're actually on the right track.
N squared.
N squared. How come?
It's from last class.
Exactly. This is 2SAT. Isn't it amazing how we've always previously solved the problems that I'm asking you questions about? It's just so it's got to be luck. So we analyzed this recurrence last time, where you move left or right by one step. And this is what's traditionally called a random walk. Okay, and we showed that the expected time to get from one end to the other was n squared. Right? And this is actually connected to what Roman said about standard deviation. Okay? If you think about it, you can think of your random walk as plus and minus ones happening, right? And if you add up a bunch of plus and minus ones, right, that tells you where you're going to land on the line, right? And it tells you where you're going to land in expectation. Right? So if I start on the left, I expect to have the same number of plus and minus ones and end up where I started. But what changes things is the variance, right? And the variance is going to be a measure of how far away I get from where I started, right? And in order to get all the way to the other end, I need the variance to be n, which means that I need n squared tries in order to get the variance up to n. Okay, so this all fits together. Okay. One more example, okay, is this lovely graph. Actually, let me draw it a different way. One more example is this lovely graph where I make a clique of n over 2 vertices. And then I hang a line off of it, also with n over 2 vertices. Now, graph theorists always have to come up with poetic names for all of their special graphs. So what should this one be called?
A lollipop?
Yes, this is the
Oh.
lollipop graph. Obviously, you have a future in store as a mathematician. All right, so lollipop graph. I just took a clique and I attached a line to it. So what's going to happen? Is it going to be the smaller of the two, or the larger of the two, or something else?
It's got to be O of n squared, right?
Why?
Well, because, it's at least, you have to go up and down the line, which is at least O of n squared.
Good. So so you're saying it's going to be omega of n squared. Because
sorry, omega of n squared.
Yes, right? You're obviously not going to cover the lollipop faster than you covered the line, and our result for the line was tight, right? It was a theta. So we're not going to beat n squared, but will it just be n squared? It turns out it's much worse. And here's why. You can think about this walk happening in phases. Basically, the hard part is covering the line, right? So, you start at this end of the line in the clique, and you try to get to the other end, okay? And it takes you n squared time to do it, okay? But it's because it takes so long to do it, it's actually more likely that before you get to the far end, you're going to come back to where you started. Now, once you're back where you started, you're in the clique again. Okay? And once you're in the clique, you don't get to try covering the line again until you get back to the start of the line. Right? So you wander around in the clique for n steps to reach the start of the line. Right? That's the expected time until you get to the start of the line. Okay. Once you start heading out on the line, you can show, and this is just a small variation on our expectation analysis, that the probability that you reach the far end before a return to the start is only 1 over n squared. Okay. I mean, you're at the start, you take a few steps away, but it's actually more likely that you'll go back to the start than that you'll continue to the far end. Okay, so it's quite unlikely that you get to the far end. Instead, you go back to the start, and then you have to do another n steps to get back to the starting point of the line again. So basically, you have to make n squared attempts to cover the line, and between each of those attempts, you're going to be spending n time. So in fact, the lollipop has a theta of n cubed cover time. Okay. So this is very interesting that you can take two graphs that have small cover times and put them together and get a graph with a big cover time. Okay. Now, what else is interesting is that this is the worst case. Turns out that in any graph, the cover time is at most n cubed. And I'll prove that to you right after we take a break. All right. I forgot to take questions before we broke. Everybody happy with where we are so far? All right. So let me now give you a general graph theorem, which is if you have an undirected graph, then the cover time is order of mn. Or as usual, m is the number of edges and n is the number of vertices. Okay. In order to prove this, let me start with a useful lemma, which is that for adjacent vertices, the commute time is at most 2m. Okay. And if I have this lemma, from the lemma, if I want to prove the general theorem, I'm just going to make a spanning tree. And I'm going to consider the time for a DFS to happen. Okay, so, I mean, I know there's a whole graph out here, and there are various edges that are not in my spanning tree, but that doesn't matter. I'm just going to look at traversals that happen, okay? So, you know, I'm going to wait and ask, how long does it take for me to, let's see how to say this. So I'm going to start up here and I'm going to ask, how long does it take me to traverse this edge? Okay. And then this edge, and then this edge, and then to come back along the edges in the opposite directions, right? And so there's this sequence of edge traversals that I'm asking about, okay? And I claim that once I have traversed each of these edges in both directions, I will have covered the entire graph, right? I cover the entire graph, right? So what I'm looking for is a sequence of vertices, right? V1 through V2n minus 1 that represents the traversal of this, the depth first search traversal of this tree, right? And this crosses each edge once in each direction. And what that means is that the sum of times is just equal to the sum of commute times on the edges, right? My HUV and my HVU might be spread out in the depth first search, but I can pull them together in order to add them up. Okay, so I'm just adding the commute times of the n different edges in the spanning tree, and so that is equal to order mn. Okay, modulo this lemma that for adjacent vertices, the commute time is at most 2m. So is everybody happy with the theorem given the lemma?
so I mean, I get the overall sort of reasoning, but I'm just not entirely convinced that the sum of times is the sum of commute times. Like, I get what's being
Yeah,
said there.
look
But
at it this way. Let me draw the edges of the depth first search. Okay? It happens in some order. And my claim is that the expected time to cover the graph is at most the expected time to do each of these traversals, to do each of these directed steps. Right?
yes.
So the time to cover the graph is at most the time to go from 1 to 2, plus the time to go from 2 to 3, plus the time to go from 3 to 4, right? And then plus the time to go from 4 to 3, and then from 3 to 2, and then from 2 to 1. Right? So I need to add things up in both directions on each edge.
Oh, okay. So I think I figured out what my issue with this is. So like the definition of the commute time assumes that you start at a state, right? And it's a time, given that you started at the state, you like go to state J and then back. It's whereas here, right, like it's assuming, well, like I'd be more comfortable about adding these expectations.
Right. The problem is the intuition of commute time is that you're starting at U, you're going to V, and then you're going right back to U.
Yeah.
Right? But this analysis is allowing you to go shopping in the middle, right? On your between your going from home to work and back, right? The point is that whatever you do in the middle, you're still going from U to V, and at some later time, you're going from V back to U. And so I'm just going to sum those two quantities to get the commute time, even though it didn't all happen at once.
Okay.
Because the definition of the commute time is just that you add these two hitting times.
Okay, that's fair. Yeah.
Okay. All right, so let's prove the lemma. Okay. In order to prove the lemma, I'm actually going to look at a new Markov chain on edges of the graph, traversed. And their direction. Okay, so a state is going to be an edge and a direction that I'm moving on the edge. Okay, so you can more easily represent or think about this by drawing directed edges in both directions and saying, right, I'm building a Markov chain on this on this graph that has directed edges. Yes? So the question is, what does the transition matrix look like for this Markov chain? So now what I'm interested in is P, so I'm traversing some edge from U to V. What sort of next steps might I be considering? What can the next state be?
Some edge leaving V.
Exactly. So I need to think about a transition from edge UV to edge VW. And what is the probability of that transition?
1 over the degree of V.
Exactly, because if I'm traversing edge UV, it means I'm arriving at V. And so the probability that I go then on VW is just the number of neighbors, 1 over the number of neighbors of V. Okay. Now, what's interesting about this is that if you write down this transition matrix, you find out that it is what's called a doubly stochastic matrix. Okay, we know by the definition of its being a transition matrix, right? That tells us that the probabilities of leaving a particular state have to sum to 1, right? And that means that the rows sum to 1 because it's a transition matrix. Okay. That makes it what's called a singly stochastic matrix. But we also have here that the columns sum to 1. Why is that?
It's a symmetric matrix.
It is a symmetric matrix. Why is it symmetric? Oh wait, no, it's not symmetric.
Oh, wait.
It's a little more complicated than that.
It's because there are exactly d of v entries that have this 1 over d of v.
Exactly, right? Exactly d of v entries have this 1 over d of v probability associated with them. Right? Essentially, right, a column sum is sort of the probability that you come from a particular vertex as opposed to the probability that you go to a particular vertex, right? And because of the symmetry of the undirected graph, these quantities sum to 1. Okay. A symmetric graph would be a graph that's regular, right? If a graph is regular, if all the vertices have the same degree d, then every transition probability is 1 over d, right? And if every transition probability is 1 over d, then the probability that you enter a vertex on an edge is 1 over d, as is the probability that you leave that vertex on the same edge. So that becomes a symmetric matrix. The probability of transitioning from u to v is equal to the probability of transitioning from v to u is 1 over d. But in a general, in this general edge walk, the graph might not be symmetric, but things still sum up properly. Okay, and the next claim is that for a doubly stochastic matrix, the stationary distribution is uniform. You're equally likely to be on every edge. And you can see that pretty quickly. If every column sums to 1, okay, and you take a uniform distribution, which has 1 over number of states in every single entry, then the product here, right? You have a bunch. You're averaging a bunch of values that are all 1 over n, and so you end up with the same uniform distribution again, right? So let's go back and sanity check that against our doubly directed graph. So what we're speculating is that each directed edge has pi sub e equal to 1 over 2 sub 2m. All right, and now let's check that. So here's a particular edge E. And there are a bunch of ways that you could end up at edge E after a single step, right? So you have some vertex with degree D, right? What is the probability that state T plus 1 uses edge E? Well, it's equal to, there are D incoming edges. And if I traverse one of those incoming edges, right, then the probability that I follow it by traversing E is, each of those incoming edges is the edge that I'm on with probability 1/2m, right? And if I traverse that edge, then my next edge is E with probability 1/d because there are D edges leaving the vertex, right? So pi sub E is indeed 1/2m. Okay? So usually I have you do that for homework, but we're not doing homework, so I did it for you. So now that we know that the stationary distribution on the edges is uniform, okay, the fundamental theorem tells us that this is the only stationary distribution, and it also tells us that HEE, the hitting time to return to edge E after you have started at edge E, is equal to 1/pi sub E, which is equal to 2m. Okay? Now, what does it mean that you have returned to edge E? It means that you start at U and traverse to V. Yes? And then what has to happen for you to return to traverse edge UV again? Well, you have to return to U to traverse UV again. Okay? So if you visit edge E, if you traverse edge E twice, it means you started at U, and then you went to V, and then you must have gone back to U, because that's the only way you could traverse the edge again. So if you traverse edge E twice, it means you did a commute from U to V and back to U. Now it's a special commute. It's a commute that used edge UV. So it's a more restricted commute. And that implies that the commute time, HUV plus HVU, which is an unrestricted commute time, is less than that HEE, which is 2m.
But isn't HEE like conditioned on the fact that we take UV in our very first step?
Yes.
Where HUV could be greater than 1, right? And that like...
Well, that's exactly the point, right? If we use HEE to measure our time, then we know it only took us one time step to get from U to V. Right? But that doesn't matter. The point is, think about this, this chain that we're looking at, or think about the vertex sequence, okay? We start at U, and then we wander around a while, and at some point we get to V, and then we wander around some more and we get back to U, right? That's the commute time, right? So the commute time is starting at U, some stuff happening, we go to V, and then we get back to U, okay? So that's the first commute, okay? Now, have we done a return to E if we do this commute? Right, so this is HUV plus HVU. Okay, but have we done a return to E?
No.
Not necessarily.
Yeah.
Right, because we might have gotten to V a different way. Okay. On the other hand, if we do this, if we visit from U directly to V and then to U, well, we've done that visit to E, but we've also done a commute, right? So it's, actually, let me write it a different way. We might do this first and then, right, visit UV and then get to V and then get to U, right? So they're all, you can break the chain into commutes from U to V, from U to V and back to U, but only some of those commutes are returns to, are start and end with E.
Mm-hmm.
And that means that the commute is shorter than the return to E, because only some of the commutes are, right, because you may have to do several commutes between U and V in order to return to edge E.
Okay, right. I think I understand now, but so maybe if I could explain it back.
Yep.
My question is the commute time, we start at U, we go to V, and then we come back to U through some path.
Yeah.
And then this HEE, we're starting on UV, then at some point we have to return to U.
Yes.
And then we also have to return to UV.
Yes.
V again.
That's
so it's
right.
sort of like in the like HUV plus HVU, we go UVU, and then HE we go VUV. Is that? Or in terms of like
UV, we go UV, UV, but yes.
Yeah, UV, UV, yeah.
Way to think about it.
Okay, yep.
Yeah. Okay, good. So that completes the proof of the lemma that says that for adjacent vertices, the commute time is linear. And you now put those together into a spanning tree to conclude that for any graph, the commute time is order mn, which of course is order n cubed, right? So the worst commute is order mn, which is of course order n cubed, okay? Which is polynomial. Okay. Now you can do a tighter analysis. If you can relate this to electrical networks. If you take your graph and you think of the edges as resistors of 1 ohm resistance, and you now ask what is the effective resistance between two vertices, that turns out to tell you the commute time. Okay, so you can have this RUV, which is the effective resistance between U and V, and then you can show that the commute time from U to V is just equal to 2m times the effective resistance. So that gives you a sort of a different way to analyze the commute times. And then you again apply the spanning tree argument to get the cover time. All right, and you can find the proof of that in the notes. It's not very complicated, but let me just finish up today by giving you an application of this, which is to testing graph connectivity. Okay, So we have fine algorithm for testing graph connectivity, right? You do depth first search, and that tells you if the graph is connected. Okay. However, that requires linear space so that you can mark the vertices as you visit them. And another complexity class that algorithmicists are interested in are complexity classes that limit the amount of space that your algorithm can use. So for any algorithm, you can ask just as well asking how much time it takes to solve a problem, you can ask how much space it takes to solve a problem. And when you formulate these questions, you assume that the input is given to you read-only, because you need linear space for that. And the space complexity questions are usually about sublinear space. So we assume we're given the graph, and essentially you can imagine that you're just given a little machine that is supposed to walk around on the graph and test whether the graph is connected. Okay? And for a long time, nobody knew how to do that. Okay? Savage gave a deterministic order log squared n space algorithm. Okay, based on sort of dynamic programming. Okay, instead of actually remembering the vertices, it sort of it uses recursion instead of dynamic programming. So it keeps computing things over and over again. But the trade-off is it doesn't have to remember too much because it keeps recomputing it instead. But randomized, we can solve this problem in order log n space. How? Well, what we just did. Just run a random walk for n cubed time. Sorry, I should be more specific. Graph connectivity asks the question of whether can you get from U to V. So this is not asking if the whole graph is connected. It's asking if you can you can reach from one given vertex to another. And so the way you answer that question with a randomized algorithm is you run a random walk for n cubed time starting at U. And you test if you can reach V, if you end up reaching V, right? We know that the cover time is order n cubed. And so that tells us the expected time to reach V is order n cubed. And so again, Markov's inequality tells us that we probably will reach V in n cubed time. So this gives us a randomized algorithm with one-sided error for deciding whether you can reach one vertex from another. And so that was a very important complexity theoretic result that comes from analyzing random walks and graphs. There are even some stronger ramifications of this, which I will tell you about on Friday. And then I will start talking about some other uses of Markov chains for sampling from complex distributions. Any final questions?
Quick question about that algorithm just now. How is it not? Where's the log n space coming in, and why isn't it like constant space?
Good question. What do you need to remember if you're going to just run a random walk for n cubed time steps?
Just like what your time step is, where you're.
Yeah, you need to remember what time it is. All right, and so you have to be able to count to n cubed.
Oh, okay.
And you need log n space to store the number, and that's the only thing you need to store.
Cool. Sorry, any chance you could go back up to the proof that it's doubly stochastic?
Yes.
I just want to look at the graph again. So the doubly connected graph, this is just the original graph, right? That we just turned it into a directed graph, right? Or
yes.
Did we? Okay.
That's correct.
And we're saying that the transition matrix for this graph is doubly stochastic.
Yes,
okay.
Actually, yes, Naveen, you're right again. Besides the counter, you also need to store the vertex you're currently on so that you know where to look in the graph.
Okay.
Right. But yes, so it's all in this picture that when you double direct the edges, basically, right, if you are one of D edges leaving, then there are also D edges entering. And each of those D edges entering gives a 1 over D fraction of its entry probability to you as an exit probability. So you also end up with this, you end up with the same exit probability as all of the entering edges.
Wait, this is a transition matrix just from any vertex, like.
No, this is, remember, this is a Markov chain on edges.
Oh, I think that's where I got confused. Okay.
Right, we're looking at these edges. So this is edge E, right? This is edge F. The probability of a transition from F to E is 1 over the degree.
Okay, that was the issue. I thought this was okay, so this Markov change on the edges itself, not on the dual of the graph. Okay.
Exactly. And that, again, we said the Markov chain on edges is uniform, and that means the probability of being on each edge is 1 over 2m, and therefore the return time for an edge is 2m.
Okay.
Right, and we did this whole analysis in terms of return times to edges, so that we could then talk about, and from there we got the commute times of edges, which we then used to look at that spanning tree to finally get back to the cover time of the vertices.
Yeah. Okay. Cool. For some reason I missed that aspect in the proof, and it confused me later on. Okay, that makes sense now. Okay. Cool. Yep.
All right. Other questions? No? Okay, I'll see you on Friday, which may be the last lecture, depending how much I get through sampling. I might go over to Monday, depending on people's mood, but we will see. Okay? All right, see you then.